All right, so we're going to introduce here our unit on probability and beginning statistics. And one thing I don't want to do is take anything for granted, all right? I know you guys have a variety of backgrounds and things that you're familiar with. I grew up playing lots of games and board games and card games and all that kind of stuff. So for me, when I would run into stuff like this, I knew exactly what they were talking about. But I understand that may not be your background, okay? So I just want to, again, not assume anything. Just make sure we understand, okay, if we talk about flipping a coin or tossing a coin, getting heads or tails, those are just the two sides of a coin. And the reason why we're going over this is because we're going to use these types of things in a lot of our problems. They're not going to be all of them, but we're going to run into these quite often, so I want you to be familiar with them. The next one is the die, or the plural is dice. Okay, so if you see die or dice, they're talking about this thing. All right, you might see people try to be helpful and they call it a number cube, and then absolutely no one knows what they're talking about. But that's a die, or if we have more than one, it's dice. And unless they tell you otherwise, it's always going to be numbered 1 through 6. Okay? But the thing I wanted to take a couple of minutes to go over with you is the standard deck of cards. We use this a lot when we're talking about probability because it's one thing that allows us to examine a lot of different possibilities. Okay? We have 52 cards total in a deck of cards. All right? And those 52 cards are divided into two colors. So we have half of them are red and half of them are black. So you can see up here we have reds and blacks. All right. Also, we have 4 what we call suits. All right. Especially if your English isn't your first language, you may be familiar with the deck but not know what the suits are called in English. Okay. The suits are spades. This shape is we call a spade. The other black one we call a club. And then we have diamonds and hearts. Those ones are a little more obvious. Okay, but those are our different suits. And because there are 52 cards, of course there's going to be 13 in each suit. All right? Now, notice each suit starts with ace as the number 1, and then it counts up to 10. And then we have jack, queen, and king. And those are known as the face cards, all right? Because they have people's faces on them. All right? So, that's the standard deck of cards. Now, if you're not familiar with those, I don't want you to get nervous that, oh great, I'm going to fail the test because I have no idea what the deck of cards is like and I've got to try to memorize all this. Okay? I will give you a copy of the deck of cards when it comes time for the assessment. All right, so let's think about what we're going to be heading into here. In the study of probabilities, one of the most significant things that you have to be able to do in order to figure out the probability of something happening is to be able to count how many different ways it could happen. All right? And also the total number of ways anything could happen in a certain circumstance. Okay? And there we're getting into a branch of mathematics that's known as combinatorics. All right? It's just a fancy term for counting. The study of counting. How many different ways can this happen? And it sounds like a really simple question, but the reality is even simple circumstances in real life can be very complex when it comes to counting how many ways could that actually happen. All right? Now, there are 3 different questions we need to consider as we're trying to count up the number of ways something can happen. All right? First question we need to ask ourselves is, does the order of the items that are being selected matter? Does order matter? Now, in our binomial probability, we ran into the combination. Okay? The combination is what we'll use when the order does not matter. We're simply making a collection of items in some sort of a group. All right? So, for example, we could be forming a team or possibly a committee. Or we could just be collecting things and throwing them all into a bag. All right? So the key here is that the items in this group do not have specific positions that we're dealing with. All right? On the other hand, we have the permutation. Okay? The permutation is an arrangement of items in order. Okay? That's the key here, that they are in a specific order. Now, this lends itself to obvious applications like, let's say, first, second, or third place. You know, if we're looking at a race, you know, what are the chances of picking the first, second, and third place winners if there are so many racers?
Either first or last.
But it can also be some things that are not quite as obvious. For example, let's say we're picking 3 people to be the president, the vice president, and the treasurer. Okay? There, it matters what order we're picking them in. Because if we're going to put one in as the president, one in as the vice president, one in as the treasurer, we could have the same 3 people, but they could hold different positions. All right? So those would be different permutations. Okay? So that's a term that you need to be real careful that you understand, is that permutations imply order. Combinations, we're just talking about a collection. So, now, I want you to think about this for a second. Which of these will have more? Let's say we're picking 3 people out of the class. Will I have more combinations or permutations? Good, permutations, because I could have the same 3 people in different arrangements. So those are different permutations, but they would all be just one combination. All right? So here's the thing. A common thing here is to mix up the formulas for these two. If you're ever not sure which one is the right formula, just see which one gives you the bigger number. That's going to be the permutation. Okay? By the way, another common thing that people refer to improperly, what do we call the kind of lock that you might put on your locker or on your bike? The master locks. They call them combination locks, right? Does it matter which order you go to the different numbers?
Yes.
Yeah. So is a combination lock a proper name for that? No, it really should be considered a permutation lock. All right, but no one knows what that is, so so people just call it a combination lock. But that's actually not accurate. Okay.
But actually, the lock we used to use is like there's a key and you press it, and there's the combination. It doesn't matter what number did you press it first.
Oh, really? So there are some that out there where you could press the numbers in whatever order you want and it'll work? Okay, so that would be a combination lock. All right, cool. All right, so that's our first question. Does order matter or not? The second question we've got to ask ourselves is, are the items being replaced each time one is chosen? And I want to take a minute or two to talk about this specifically, because this is going to be a big deal when we're talking about a problem, and it can really change the entire way we approach a problem. Okay? So I've got a deck of cards here. What are my chances of picking out, say, the ace of spades?
152.
Yeah, there's 52 cards. You know, so the ace of spades, we got a 1 out of 52 chance of finding it. Okay? Or even less if we're actually looking for it. There it is. Okay. So we found it. So there's our ace of spades. Now, let's say I'm picking out 2 cards. All right? We just said my chance of finding the ace of spades is 1 out of 52. Let's say I pick out a card, and I pick out the ace of spades.
151.
Okay? Where did I put it?
I think we could just pass it.
I shouldn't have.
I think we pass it.
There it is. Okay. So let's say I found it on my first try, and I set it down here. Now what are my chances of getting the ace of spades?
0.
0 out of 52, right? I found it and I didn't put it back, so now there isn't one in here anymore. So I don't have any chance. And in other words, the number of ways I could get it changed because I did not put it back. All right? Now, let's say I pick a different card. Okay? All right? I pick out a random card. Here's the 8 of hearts. I had a 1 out of 52 chance of getting the ace of spades my first try. Now I picked out the 8 of hearts. What are my chances the second try?
1 out of 51.
1 out of 51. Again, it changed, right?
Yeah.
All right. So, when I don't replace it, my probabilities change every time. Okay? However, if I pull out, there's the ace of hearts. The first time I had a 1 out of 52 chance of getting the ace of spades. If I put that card back in and shuffle them back up again, my chances the second time are still 1 out of 52. Okay? And here's the cool thing about that. Even if I got it the first time, what are your chances of getting the same card twice in a row?
1 in 104.
Okay. Well, you've got a 1 out of 52 chance of getting it the first time, and if you put it back, you've got a 1 out of 52 chance of getting it the second time. Okay? You really have no better of a chance or no worse of a chance of getting the same card the second time than you do of getting any other card. Okay?
How would you figure out, before you picked out that first card and you knew the probability was 152, what would you say, before you took out 2 cards, what would be the actual odds of you picking out the ace of spades twice?
Ace of spades twice? It would be 1 out of 52 times 1 out of 52. Yeah. Now, what we're talking about here is the idea of things being independent or not independent. Okay? Independent events are events where the first one has no impact on the second one. So, for example, when I put it back in, all the probabilities stayed the same the second time. Okay? So, when you see with replacement, they're telling you, hey, these are going to be independent. Okay? Again, the probabilities do not change from one step to the next, or from one event to the next. Okay? Other examples of this could be, say, I roll a die. What's the chances of getting a 4? 1 out of 6. So if I get a 4, what are my chances then of getting an ace of spades?
Oh, it's still
It
1 out of
doesn't-
52. You didn't.
Yeah, it's 1 out of 52, right?
Yeah.
Rolling that die is not going to have any impact on which card I pick. Okay? So, those would be independent events. Okay? Rolling a die and picking a card. Okay? Yes?
But taking a card out of the deck is not considered an independent event. Like,
Yeah, if we pick one and then we remove it, we just changed all the probabilities for all the other cards. Okay, now it's a 1 out of 51 for everything else. So, now independence is really important, especially in the future as we look at the binomial expansion applied to probabilities. That only works if we have independent events, as we'll see a week from Monday. Okay? So, that's where we're headed with this. Now, another concept that we have to think about, the question we can ask ourselves is, can different outcomes occur simultaneously? You might say, well, how in the world could that happen? Well, let's think about this. Let's say that I was looking at my chances of drawing a heart. Okay? If I pick a card out of the deck, what are my chances of actually getting a heart?
13
1 over 4.
Yeah, 1 out of 4, because there's 13 hearts out of the 52 cards, and that's 1 out of 4. Shouldn't have a equal sign there. Okay? Now, question. What are my chances of getting a face card?
Oh, that is a heart, or that is
No, just getting a face card.
There's
12 out
no
of 52.
Yeah, there's 3 face cards in each suit. There are 4 suits, so that would make 12 face cards out of 52. So good, that would be, what is that? 3 out of 13.
Yeah.
Duh. 3 out of 13. Now, question. Is it possible to pick one card that would fall into both of those categories?
Yeah.
Yes.
It would be 3 out of 52, right?
Yeah, like if I pick the Jack of Hearts, that's a face card and it's a heart. Okay? So in that case, these two events, drawing a heart and drawing a face card, could occur simultaneously. They could occur on the same draw. Yes?
Why does it say it can't?
Well, mutually exclusive, these would not be mutually exclusive. Okay?
Why?
Because they can happen at the same time. Alright? So, these would not be mutually exclusive. Alright? However, let's again take the face card, 3 out of 13. Okay? And let's say I wanted the probability, what are my chances of drawing a 5?
I'm getting a 5.
Okay?
I'm getting a face, no, you can't do that.
4 over 52.
Yeah, there are 4 5s in the deck, so it's 4 out of 52, which is 1 out of 13. Okay? Now, if I draw a card out of the deck, and I got a 5, is it possible for it to also be a face card? No. Okay, because the face cards are only jacks, queens, or kings. So, these would be what we call mutually exclusive events.
That can happen separately.
Okay? It's impossible for one event to have both outcomes at the same time. Okay?
I'm sorry, could you explain one more time?
If two things are mutually exclusive, it's impossible for both of them to happen at the same time. Okay? Let's think about flipping a coin.
Yeah, I was just
If you flip a coin, it's impossible to get a heads and a tails on the same flip, right? You can't get both. Those are mutually exclusive events. If you roll a die, it's impossible to get a 1 and a 5 on the same roll. Okay? Now, with a die, it's possible to get a 1 and an odd number. Okay? Or, if your events were a 5 or a prime number, you could get both of those at the same time when rolling a die. Okay? So you have to really think about the events that you're looking at and see, could they actually happen in the same event? Okay? All right. So I'm defining a lot of terms here, and in this unit, it's going to be very, very important that you understand those terms. Okay? If there's ever any term that I use that you don't know what I'm talking about, you need to ask right away. Okay? This whole unit is going to be very language intensive. In other words, you got to really read carefully. One word could make the difference, the whole difference in how you interpret the whole problem. Okay? So you have to read very, very carefully. And if you're having trouble with that, you need to come and talk to me and we can work on that together. Okay? All right. Now, the last thing I want to look at today is this fundamental counting principle. All right? The fundamental counting principle. You can see it written up here. It says let E1 and E2 be two events. The first event can occur in M1 different ways. So there's that number of different ways that event could occur. After that, E2 can occur in M2 different ways. All right? So these are just two different numbers. Here's the key to the whole thing, the whole principle. It says the number of ways that the two events can occur, we're talking about occurring together, is M1 times M2. Okay? M1 times M2. So I give you this example here to illustrate and to help us understand what this is talking about. All right? Suppose we pick two cards from a deck, replacing the first one. So what does that tell us we're dealing with?
Exclusive, not exclusive, the replacement, yeah.
We're replacing. Okay, these are going to be independent events because we're picking a card, we're picking out a card, and we're putting it back. So nothing has changed from the first draw to the second draw. Okay? How many ways could you pick a diamond the first time? Okay, so let's stop there. How many ways could you pick a diamond?
1 and 4. 1 4.
No, not probabilities. Now we're talking about counting. How many different diamonds are there? There's 13, right? So there's 13 different ways you could pick out a diamond. All right? And then, and a face card the second time. So how many different ways could you pick out a face card? 12 ways. Okay? So now, according to this, how many different ways could we pick a diamond followed by a face card?
13 times 12.
Very good. We're going to multiply. It's 13 times 12. Okay? So there is actually 156 different ways that you could do that. You might say, well, how in the world do we get that many different ways? Well, let's think about this, okay? Here I have all of the diamonds on the left and all the face cards on the right. Let's say we draw the 6 of diamonds first. Okay, so here's our 6 of diamonds. So I draw it, I've got a diamond, and I put it back. So the next card I draw, if it's one of these 12 ways, I could draw the King of Hearts. Or I could draw the King of Spades. There's 2 ways. Or I could draw the King of Diamonds or the King of Clubs. There's 4 ways. Or the Queen of Hearts, or the Queen of Spades, or the Queen of Diamonds, or the Queen of Clubs, or the Jack of Hearts, or the Jack of Spades, or the Jack of Clubs, or the Jack of Diamonds. So you'll notice here, just from drawing that 6 of diamonds first, I have 12 different possibilities. Okay? Now, since there are 13 different cards that I could start with, and each of them is going to have 12 different possibilities, that's where we get the 13 times 12. Okay? So that's where this fundamental counting principle comes in. All right? Let's think about another example here. All right? Let's go get some ice cream. What?
Does that one take into account if you pick a queen diamond, a face diamond?
Can someone answer that? Think about that, because that's an excellent question. Can you say it again?
Does it take into account if you pick a face diamond?
Like if you pick the jack or queen or king of diamonds,
Yeah.
would you only have 11 options after that?
No,
Still be the
because you're
same.
still putting it back.
There's the key. Notice we're putting it back.
Including
All right? We're putting it back. But hey, those are the kinds of questions you've got to ask when you're doing stuff related to combinatorics and probability. All right? It's an excellent question.
We're getting some ice cream now?
All right, so let's get some ice cream.
Alright.
All right? You walk into the ice cream shop and you are faced with lots of choices. All right? What are some of the choices that you are faced with?
Chocolate, vanilla.
Okay, so flavor, right? Flavor. We'll put that in the middle because that's the most important. All right, flavor.
Size.
What?
Size.
Sides, good. Or sides or toppings, right?
This are On the
The
top.
size of the
No,
cup.
I mean the size of the cup.
Oh, the
Is
size.
it like double bowl or single bowl?
Okay, yeah. A double scoop, a single scoop, or whatever. We're actually going to leave that one out because that makes our problem even more complicated. Okay? We're going to assume that it's just one flavor, one scoop. Okay? What's the other thing we can decide on?
how many sides?
A cup or cone?
Okay, yeah. Whether we're going to get it in a cup or in a cone or what kind of cone. You know, we can get it in a regular cup, or we could get it in those like cake cones that kind of taste like styrofoam. We could get it in a sugar cone.
Waffle cone?
Yeah, waffle cone. You could even get it dipped in
We
chocolate.
gotta stop, I'm getting hungry.
Yeah.
Okay, chocolate dipped cone. All right, you've got a lot of possibilities. So there, just in how you're going to get the ice cream, you've got 5 different choices, right? All right, so how many flavors? Let's say we're at Baskin Robbins. Do you know how many flavors they've got?
26, 32.
Allegedly? You can just stick it there, thank you.
13.
There's one for every day of the month.
31.
30?
31 flavors. That's like their thing, you know, the 31 flavors. So you have 31 flavors to choose from, and then about how many sides do you, or how many toppings do you think?
12, something like that, maybe more.
12?
M&M's, whipped cream. fudge,
There's lots.
caramel.
You want to go with 12?
I'm daydreaming right now.
Okay. Let's say that there's 12 different toppings to choose from. And by the way, we're also going to just consider one topping. Because if we considered, all right, what if we didn't get any toppings, or what if we got 2 toppings or 3 toppings? We just made the problem like 10 times harder. All right? But just with this level of simplicity, how many different options do we have?
31 times 12.
85.
Good. 5 times 31 times 12. All right? And what does that come out to?
185.
What did you?
185.
No, it should be more than that.
Oh, no.
60 times 31, which is 1,860.
I think that's right. 1,008. Okay, 1,860. All right. So guess what? You could go to the ice cream shop
Oh my God.
almost every day for almost like 6 years and not order the same thing twice. Okay? But that's how many different possibilities you have.
So
Okay.
Same for the first one? No.
And it's just the fundamental counting principle. All right? But guys, this can be used for lots of different stuff. let's say you're trying to figure out how to get from here to the airport. You have 3 different options, or you have to go to the airport and then you have to go from the airport, you're flying back home. Okay? So let's say you have like 4 different options. You could get a friend to drive you, you could get an Uber, you could take the train down there, or you could just get a taxi. Alright, so you have 4 different possibilities. And then there's 6 different flights that you could take that would all eventually get you back home. So how many different ways could you get back home?
Wait, did you say there's 3 different ways to get to the airport?
24. We said there are 4 different ways. Yeah, 4 different ways to get to the airport, 6 different flights. There's 24 different routes or different ways that you could get back home if you were flying home. Okay? So, it's cool stuff. That's where we're starting here.